PhD candidate at the Stony Brook University working under the guidance of Professor Anshul Gandhi. Today I'll be talking about our work on finding the optimal configuration for distributed applications implemented using the microservices architecture. The microservices architecture allows applications to be decomposed into different interacting modules, each of which can then be independently managed for agility, scalability, and fault isolation. Hence, distributed applications implemented using microservices architecture are quickly replacing existing deployments implemented using monolithic or multi-tier architecture. Performance in these applications is crucial as these are usually customer-facing applications. However, performance depends on the configuration of the application, which makes finding the optimal configuration a very important problem. But with microservices architecture, the problem of finding the optimal configuration is made difficult by the following reasons. Very large configuration space. There are so many microservices involved, and each of them have so many parameters that the configuration space is very large. Interdependent parameters. The value of one parameter can influence the value of another parameter, hence it's important to jointly tune all the parameters. Non-linear relationship between microservices parameters and the performance. The performance need not have a linear relationship with the parameter values, making it difficult to find the optimal value for the parameters. Given these challenges, it is difficult to find a functional form that captures the relationship between configurations and the performance. However, for a given configuration, the performance can be measured by applying the configuration, bringing up the application, running an experiment. Hence, we frame the problem of finding the optimal configuration as a black box optimization problem. Coming to the goals, we analyze the performance of different black box optimization algorithms, propose and analyze different ways to reduce the dimensionality, and we also develop a framework to perform the above conveniently. Coming to the system that we use to run our experiments, the user provides the details about the application in the application deployment file. The controller takes the application deployment file and the configuration chosen by the optimizer as input and generates the Docker Compose files. The Docker Compose utility takes these Docker Compose files and brings up the application. Once the application is up and running, the client generates the workload. The controller collects the metrics and passes it on to the optimizer. The optimizer then uses this metrics to generate the next configuration. This process stops when we run out of budget or when we have reached the required performance improvement. Coming to the application that we use social networking application from the Delta bench. We deploy the application on 4 servers, each with 24 hypercores, 40 GB of memory, and 250 GB of disk space. This is a list of optimization algorithms that we use in our work. We request you to read our paper for more details. Since having a large state space is one of the critical issues of finding the optimal configuration, we propose and evaluate different dimensionality reduction techniques. The first one is the critical path technique. The critical path technique is where we suggest tuning only microservices that determine the latency of the request. Coming to the non-bottleneck technique, we suggest tuning only those microservices that are probable bottlenecks of the distributed application. Coming to the performance variance technique, we suggest tuning microservices that have significant service time coefficient of variation. Figure shows the performance improvement in tail latency of the social networking application under different dimensionality reduction techniques compared to the tail latency when using the default configuration for all the parameters. For ease of illustration, we show the results for 2 specific optimization algorithms, the dynamically dimensioned search and the Bayesian optimization with Gaussian processes, the surrogate model. We see that tuning all the 28 microservices of the social networking application provides about 25% improvement in tail latency, whereas using our dimensionality reduction method of critical path, we see around 23% improvement. We see similar improvements in non-bottleneck technique. Coming to the variability technique, we see around 20% improvements. Coming to the comparison of different algorithms, the bars in the figure show the sorted percentage improvement in tail latency over the default configuration afforded by different optimization algorithms using the critical path dimensionality reduction technique. For comparison, we also show the improvement afforded by the configuration employed by the Delta benchmark developers. We have labeled this the DSB. We also show the serial performance improvement afforded by the approach that sequentially tunes each microservice on the critical path as opposed to jointly tuning all the microservices on the critical path. To evaluate the overhead of different optimization algorithms, we plot the time taken by the optimization across all the iterations. We see that DDS provides the best improvement of around 24% and also takes the least amount of time. Based on these, we conclude that DDS is the best performing optimization algorithm. An additional advantage of DDS is that it is designed for optimizing in high dimensions, making it suitable for enterprise applications that are composed of a large number of microservices. These are the list of future work that we would like to explore. Thank you.